Okay, so welcome back after lunch. So between now and 2:30, we have a few, let me start off with a few slides and finish off what I had in terms of slides, which will take about 10 to 15 minutes, let's say 15 minutes. And then after that, we have a hands-on that we can continue until 2:30. There's 2 or 3 hands-on exercises. If you can get through one, that itself is good, and the others are just variations on that one, which you can do later. So before lunch, we covered the fence synchronization, which, as I said, was collective over the entire group of processes, and that's a potential performance issue if you don't need to synchronize over everybody. So there is a second version that is not collective over the whole group, but you can define subgroups of processes and do the equivalent of a fence across them. It's just that it's split into different functions with different names. It's called post start complete wait. And yeah, so on the target side, the process calls MPI win post and win wait, and on the origin side, it calls something called MPI win start and win complete. The one issue here is that the parameter it takes is an MPI group object, which very few other MPI functions take a group object. They take a communicator otherwise. The only tedious part of this using this is that you need to create a group. So a communicator contains a group of processes in it, and it also contains something called a context ID. So you don't see a group object normally. So you have to use MPI group include and group exclude functions to just include the set of processes whom you want to synchronize with, and create the right group containing processes on the other side. So let's say you're doing a stencil computation and your nearest neighbors are up, down, left, and right. Your group is just that set of processes, and you have to define it with the right group parameter, and then your synchronization is reduced to a smaller set of processes. It tends to be less used in practice, this one, partly because of the it's sort of a little tedious to create these group objects and use this. Instead, there is a third method. Why is this not at that? Yeah, I'm going to skip the example for now. There is a third method which is called lock and unlock, and that is easier to use. It in fact doesn't need participation from the target side. Its semantics can be a little different, but this is probably the most widely used, particularly the lock all, unlock all type of model, which is on the next slide. So this synchronization method is called a passive target synchronization, because the target is completely passive in this operation. It does not call any data transfer function, and it does not call any synchronization function. The synchronization is all called on the origin side via the lock and unlock operations. And the lock and unlock is a sort of an unfortunate choice of terms here. You're not really acquiring or releasing a lock. You are just starting a series of one-sided operations with a specific rank. So lock takes it should be on the next slide. Yeah, the win lock takes a lock type as an argument. It is either a shared lock or an exclusive lock. It takes the rank of the target, and there is an assert which can be used for some performance optimizations that we won't cover here, but they are in the standard. And then the corresponding unlock is just the rank and the win. So when you do a lock put unlock, what it does is you get access to the how should I put it, to the target memory, and it's either in a shared or exclusive state. That is, if there is another process also doing a lock and unlock to the target, and if one process has, if both of them have chosen a shared lock, then their puts and gets can happen in an interleaved manner at the target window. If they choose an exclusive lock in the lock type argument, then it will be ordered in some way. One of them will, their entire set of operations between the lock and unlock will happen first, and then the other, and they won't be interleaved. And there is also a flush operation, which I think is on the, well, no, I don't have the slide on that. It's just listed on the bottom. There is also something called MPI win flush, which you can call within the passive target epoch if you want to temporarily, if you don't want to release the lock, if you want to complete operations before releasing the lock, you can call MPI win flush. Win flush completes the operation both locally and remotely. Win flush local completes the operation just locally complete. You don't know whether the data has been deposited at the target. So one thing to note here is when you do a lock put unlock from the origin to the target does not know when this operation has happened, because the target does not participate in it. It does not call any MPI function to participate in it. In the fence model, it does. It calls the MPI win fence. So when it returns from the fence, it knows that the RMA has completed. So some other way, if that process needs to know that the RMA has happened, there has to be some other way of some out of band way. It could be algorithmic. There could be by the nature of the algorithm, it is known, or you could have, I don't want to say barrier, but you could have some other way of a handshake or synchronization where the other target needs to know, or this process could set a value at the target, and the target could check that value, and it has to be done making sure that it's just not checking the register value, that it's not just cache. We have to define it as volatile or something, so that if you're checking a flag, you're actually getting the new data that somebody else may have written into. But this is truly one-sided in that the other process does not even do any synchronization. And a new function that was added in MPI 3 is a lock all and an unlock all. This is quite useful because it does not take a target rank as a parameter. So you're effectively getting a lock on all other ranks in the window. These are shared locks. There's no exclusive lock here. So this combined with the win create dynamic, if you do use the win create dynamic and then attach and detach memory as needed, and use the lock all and unlock all. So you could use this lock all and unlock all just once in the program, and use with the dynamically created windows, you can do one-sided communication quite dynamically, and when combining it with the flush all type of primitives to know that the operation is completed. So this model finds some amount of usage compared to the other two, because it makes the one-sided programming easier. So then, okay, are there any questions about lock unlock before I move to something else? Anything in the chat?
I think one question is there any performance difference between active and passive synchronizations?
Yeah, there is a performance difference in the sense that MPI win fence is collective, so that can it's almost like a barrier. It's you shouldn't. I don't want to say that because it can be misunderstood, but it's a collective function where everyone needs to reach the fence before they can leave the fence, at least in most cases. There are some exceptions to that. So that is a performance issue. In the lock unlock model, the other side is not involved in there. So that can be truly one-sided as long as there is something causing progress underneath. It could be hardware progress, and we have a few slides on that in a little bit about progress in one-sided communication. Anything else?
I think that's all the questions.
Okay. There's one issue that I want to mention, and you don't need to worry too much about it because it can get a little complicated, is the notion of a memory model. So the MPI RMA has two memory models. They're called separate and unified. Originally in MPI2, there was only this the separate model, and it's the most general memory model, and it's intended to work even for non-cache coherent architectures, which there were one or two at the time of MPI2, but later on, many of them didn't need that level of that kind of model. So a simpler model, a unified model, was defined in MPI3. All it means is that when you're combining local loads and stores with RMA operations. So for example, if I do a lock put unlock to a target, how can the target read that location? So in the separate model, it was required that the target itself has to do a lock and then even just for the local read, like a load operation, not even an MPI function, just a local load, it needs to have a lock unlock around it because the memory may not be cache coherent. The unified model simplifies that. It says that it's effectively as if there is a coherent memory, and one of the target will just be able to read it. And there are some more details surrounding this. And you can, in your program, you can query whether this implementation or the platform that you're running on supports the unified or the separate model, and then write accordingly. In most cases, that unified model is the one that works, and that's why it was added, to make the programming simpler. Yeah, so this just explains the same thing with the way it is defined in the standard. That the standard says that assume that your window memory actually has two versions of it, a public version and a private version. And in the separate model, you need to take some steps to make that private version consistent with the public version. Whereas in the unified, there isn't a separate private and public. There is like one version which automatically is updated. This is just some detail. If you ever get into that portion of the MPI RMA chapter, this might help you at least get started with it. But for the most part, at least initially, we don't need to worry about this a lot. There was a question on chat before I started about how to use the win allocate shared with direct loads and stores, since you get direct access to shared memory, at least within a node there, and whether you need to use synchronization. So I don't know if that got answered, but I think Yanfei has a section on MPI plus shared memory, and so some of that will get covered there, and it also ties into this memory model issue. Or you can even, once you get that shared memory with win allocate shared, you don't even need to use MPI. You can do direct loads and stores, and you can do your own mutexes or semaphores among processes to coordinate access, and just treat it as shared memory. It's like instead of getting a POSIX or System 5 shared memory, which it's a little complicated. This is can be an easy way of getting shared memory if that's what you want to do. But I'd say if that question is not yet answered, let's get to the MPI plus shared memory part of this, and then see if those concerns are addressed there. Okay. Yeah, this is just some more about the memory model, which I'm going to skip in the interest of time and give you more time for hands-on. Yeah, there's an MPI win sync function that can be used to synchronize these public and private copies in the separate memory model. Okay, this is just one more example, which also we will get to. Okay, so just a few more slides about how does the communication actually take place? Does hardware help you? Is there a progress thread and associated performance issues? So about hardware offloaded communication, if you're doing two-sided send and receive, then doing it entirely in hardware is a little difficult because it requires the message matching that's associated with send and receive. A send has to match a particular receive, which is specified by the rank, a tag, and the communicator. So for this to be directly available in hardware, it's a little difficult. There might be there might be some things that do a subset of it, but there is some software needed on top of that. Whereas the one-sided, because it doesn't have this matching requirement, it can more directly be done in hardware, and so less overhead in a software layer or at the MPI layer. And there are many networks that support remote memory access directly, such as the InfiniBand or the Cray networks, the Aries or Slingshot, and also in the Fujitsu Tofu network. So it's a better match for hardware. And some of the design decisions, such as the fetch and op, compare and swap, are also designed in a way that can be directly layered on top of hardware with minimal additional overhead. So the next thing is about asynchronous execution of the RMA, or even of non-blocking communication in general. I think there was a question on Slack in the morning about iSense. Is there any performance benefit? Does it really happen in the background? And that ties into something called progress in MPI. So the MPI has a notion of when does progress happen in an MPI implementation. By progress means some forward movement on a communication operation. Either the data is being sent out, or some matching is happening, or something. So in the absence of any additional threads in the MPI implementation, progress may not happen until you make an MPI call, because that when you make an MPI call is when you get into the MPI implementation, where in addition to the operation you have requested, it could make progress on some other pending operations that were there, some previous sends or receives that were posted, iSends, iReceives, that are still pending. It could do progress on that. It could do something else. So in the absence of any background thread in the MPI implementation, progress may not happen until you call some other MPI function. But many MPI implementations nowadays have a progress thread. You can call it a helper thread, or they have different names for it. They may not enable it by default, though, because there is some overhead associated with that. It might need a thread safe MPI init. You might need to specify a thread safe level, like thread multiple for it. Maybe not, depending on how it's implemented. Plus, when you have a helper thread running on the background, that consumes some resources. Unless it's actually sitting on a separate core, it might interfere with your main thread. And if there is a separate thread, then all the communication has to go through thread safe mechanisms. There might be mutexes involved. So your latency of a 1 byte send or a very short message, that could be higher if you enable this thread, the thread-based progress. So that's why it's made an option that if you really feel that your non-blocking communication is not progressing when you expect it to, then enabling this thread might help you. And there are ways to enable it. So there's usually a environment variable or some other way when you're before running a program. It could be before even building the MPI implementation. It depends. There you can look at the documentation, and there is a way to enable that. And as a second bullet says, the core binding is important to make sure that second thread is not interfering with your main primary thread of computation and communication. Another way is, if such a thing is supported, is by the hardware interrupts. That is, the communication in an incoming message uses an interrupt to awaken a kernel thread, and then that interrupt handler takes care of that message. So you could find some examples of it. So the Cray MPI had it in some version. The IBM had it on the BlueGene P, but you need hardware support for it, and it's not commonly found. Another approach, which is more of a research project, this is a research project that was at Argonne by Mincy and Pawan Balaji were involved in it. It's called Casper, where instead of using a thread, it uses additional processes. These are host processes. These are not part of your normal MPI program. So, and it uses the PMPI profiling interface to trap the MPI calls, and you run the program with one or more additional processes on the node, which are not doing anything other than assisting with this one-sided communication. And it works for the win allocate type of windows, where the memory gets allocated in shared memory. So these additional processes can directly write into that shared memory. So by trapping the MPI functions, when you do a put or a get, instead of it going to the target, it goes to this additional host process, which does the communication for you, and it can access the process, the real target's memory, because it's that window is in shared memory. It can directly access it. And this ghost process is not interrupted. It's not off doing computation and therefore not available. It's, there's always like a background MPI receive posted that's never going to get fulfilled until the very end. So there's always a periodic MPI progress happening. And using this kind of method, they were, and if you're interested, there is a way how do you download this package and use it. And using this approach, a process-based approach rather than a thread-based approach, they were able to get good performance. That is because the progress kept happening in the background, and taking advantage of the additional cores that may be there on modern multi-core systems. So with this one on the lowest line, the gray line is the time with Casper, and then the orange one is with threads, and the blue one is without either of this. And because the progress didn't happen in the background, that blue line took a lot longer. And there's just some more data on this. So just one last slide on summary before we go back to the hands-on. So MPI, the one-sided, the concept is simple. You create a window to expose memory. You decide which synchronization mechanism you're going to use, and then you do your puts and gets to get the data. And the unlock is the one synchronization is probably the one you should try to use in your real applications, because the fence can be synchronizing across many processes. Or you can use the lock all, unlock all, which is even more general. So let's switch to the hands-on. And are there any questions in chat in the meanwhile? Janfe, is everything answered?
Yeah, questions are, we were handling it.
Okay, good. So there are, we have a couple of 2 or 3 hands-on exercises. You won't be able to finish all of them till like 2:30 or so. But the first one is, let me just go to here. You start with the one with the derived data types. That's the solution for the derived data types hands-on that was in the morning. So that's in the derived data type stencil.c directory. And instead of the send and receive, use the fence synchronization and use MPI puts. And so this is because it's easiest. I mean, it's not the best way of doing it, but you'll get to use MPI window. You'll have to do a win create or a win allocate, and then you have to call MPI fence, and then you have to call put with the right parameters so that the address for the origin buffer and the address for the target buffer are correctly passed there. The data types are already available. This example has already created the data types for you. So it's a question of replacing the I send, I receive with fence and put, which is relatively straightforward. And if I show you the figure, what you're doing is whatever was being sent with an I send, you're now sending it with a put, except that you need to know where to place it in the target buffer. So the green the green areas here are the target buffers, and you need to pass the target values in the put call correctly so that it goes into the right location. That's the only tedious or tricky part. Rest is similar. Instead of a put, you could do a get as well. It's just the opposite of a put. Only the address is changed. So here, instead of sending from the red to the green, you are receiving from somebody else. I mean, it's not shown here, but you're receiving from a red into a green effectively. The get is just the reverse direction. So it's only the address that is different. And the third exercise was to do the same. Instead of fence, use lock all, unlock all. The one trick there is in the lock all, unlock all, the target does not know when that operation has happened. So in your stencil, that the process does not know when the operations directed to it were completed. So you need some other, like a barrier or something there, just for it to know that. So it's not a good use of the lock unlock model, because you need an additional barrier or something there to know that the RMA has happened. But it's an exercise just to get familiar with this code. And as this slide says, all the solutions are available. So in the RMA directory, the stencil fence put has the solution for this. But I'd say you can take a little bit of help from it and avoid looking at it right away, I would say. And similarly, there is a get example as well. And similarly, there's the lock unlock example as well. So the answers are there. I would say try doing it yourself first, and we are there to answer questions.